Well, today we're going to find a rather marvelous result that shows that this important vector line integral we've been doing, it computes work and so forth, can actually be evaluated as a double integral over the region encloses, a particular double integral. This result, kind of startling I think, is due to George Green, a famous British mathematician, mathematical physicist actually, who was almost entirely self-taught. He only got about 1 year of formal schooling between the ages of 8 and 9. Here is a brief Wikipedia article that I think you might find interesting reading if you find today's lecture useful. He wrote an essay in 1828 on the application of mathematical analysis to the theories of electricity and magnetism, laid the foundation for James Clerk Maxwell's later beautiful theory on electromagnetism that underlies almost all of our electrical devices today. So he's sort of laying a foundation for what led to practically all the electrical devices we have today. It didn't live very long, as you can see. Well, let's see how this result actually applies to us. Here's the notes that I put out online so you can download these and get all these and look at the rest of the lecture with these if you want. Recall our previous methods to evaluate this line integral that we're going to now see how Green's result relates it. Our previous methods were two. Right? If we had a vector field along a curve C, and we wanted to find the line integral of that vector field, we could evaluate it as f dot dr dt dt. This is our fundamental result by which we evaluated almost all line integrals. Now, a second result was, if that vector happened to be a conservative function, the gradient of some potential, phi, then we could just take phi at the final point minus phi at the beginning point and evaluate the line integral that way. That's an extremely important concept in work. It's the work energy theorem. However, sometimes this is hard to evaluate, and you may not be able to find a potential. In the special case that you're in a plane, this only applies in 2 dimensions, and it's a simple closed curve traversed counterclockwise or clockwise, because you can just take the minus this result. You can apply a nice result called Green's theorem. And here it is. Green's theorem says this: if a plane region R is simply connected with its boundary, a simple closed piecewise smooth curve, taking counterclockwise, and F, the vector field, it has continuous components, F and G, on an open region containing this region R and its boundary, then the usual work integral around this simple closed piecewise smooth curve is equal to the double integral of dg dx minus df dy, where g is the second component of the vector field and f is the first component. So you can compute the work around a simple closed curve by evaluating a double integral over the inside. Boy, that seems like we're going backwards to turn a single integral into a double integral. But amazingly, this is actually pretty useful in a lot of situations. For instance, if this region happens to be a circle, it might be easy to do the double integral, easier than running along the boundary, if it's a rectangle or a triangle or something like that. Also, once in a while, you want to go the other way, and then you're taking a double integral to a single integral, so you've reduced your number of integrations, right? So now I just want to point out also another way this theorem is often written. This is just the same theorem. Is, remember, you can also use the notation for integral f dot dr as little f dx plus little g dy, where little f and g are the components of the vector field f. So again, this only applies to simple closed piecewise smooth curves, so they have to go around a circle, finish where they begin, and you want to take them counterclockwise so you get minus this result. and in the plane, only in 2 dimensions. We will get a corresponding 3-dimensional result later in Stokes' theorem that makes this a special case of it. All right, so we want to find the work done, suppose, by a force that's x minus y cubed I plus y plus x cubed j taken around the unit circle counterclockwise. Oh boy, how much work is done around there. It's too bad we don't know it's a conservative force. If it happened to be conservative, then the integral all the way around would be obvious. It'd be 0, right? The work by a conservative force around any simple closed curve is 0. All right, because you take the potential at the end point minus the potential at the beginning point, but the end and the beginning are the same on a closed curve, so you get 0 work if the force is conservative. All right, so now, for this one, we'll say the work is integral f dot dr, where we can now apply Green's theorem and say this is equal to the double integral over the region enclosed, which is the disk, right, inside the circle, dg dx minus df dy, where g is this component and f is this component. So we take dy plus x cubed dx minus dx minus y cubed dy over the disk, and we turned our single integral into a double integral, but that's not actually so bad because this was a mess to integrate, and this one is not so bad. If you take dg dx at 3x squared, take df dy at 3y squared, and you're only integrating over the unit circle, so that's actually not too hard to do in a double integral. In fact, 3x squared plus 3y squared is 3r squared. I can pull the 3 out. Now I integrate over the unit disk, r squared, multiply the result by 3. Well, integration of the unit disk, you can put it in polar coordinates as r going from 0 to 1, theta going from 0 to pi, r dr d theta. So now we have to integrate r cubed from 0 to 1, and we can, since these are constant endpoints, we can pull this out and write it as the product of the 2 integrals. So integral of r cubed from 0 to 1 has the integral of 1 going from 0 to 2 pi d theta gives us 2 pi times, let's see, that should have been a fourth. I'll have to fix that on the note. A fourth is 2 pi over 4 gives us pi over 2. Let me fix that one here. So the result is pi over 2 for this line integral. And since the result isn't 0, obviously the force was not conservative that we integrated around that path. Well, here's the next result. Suppose I have a different region. Suppose I want to integrate around this unit square. And this time I'm going to go clockwise instead of counterclockwise. I want to integrate minus y dx plus x dy. This is the second form you see Green's theorem. And this is also integral f dot dr, where f is the vector with components minus y plus x. It's just written in the other form. So by our previous theorem, we can try and write minus y dx dt plus x dy dt and integrate around this path, but we'd have to break it up into 4 pieces, right? We'd have to integrate, we'd have to parameterize this, 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 and this. So theorem 1 would apply and would do this, but with 4 integrals. Maybe we can do it easier with Green's theorem since it happens to be a simple closed curve. So we'll say integral f dx plus g dy is equal to dg dx minus df dy. If it's counterclockwise, well, if it's clockwise, remember the vector line integral is just minus the result going the other way, and so we just take minus Green's result, minus the integral dg dx minus df dy, will give us the integral for the clockwise line integral. So now we have turned our single integral into a double integral, but once again it's very easy because it's just a unit square, right? We go, x goes from 0 to 1, y goes from 0 to 1, and dg dx minus df dy is particularly easy, right? F is whatever multiplies dx, g is whatever multiplies dy, so dg dx is 1, df dy is minus 1, and we just have to integrate 2. How easy? I know what this is. I just integrate from 0 to 1 and 0 to 1 minus 2, and I get minus 2. So there's this line integral evaluated easily by Green's theorem because we happen to be going around an easy square. And this probably actually saved this work despite that we went from a single integral to a double integral. Now, let's move this up. It gets a little harder. These results are really nice for engineering. People in electrical engineering may want to pay attention to this. Green's theorem, despite that it applies to the simple closed piecewise smooth curve. What did that mean? Simple means not self-intersecting, recall. Closed means it ends where it begins, so it's not self-intersecting except that it ends where it begins. Piecewise smooth means you can break it up into a finite number of pieces, each which has a continuous derivative along it. And so that's the kind of curve we're talking about. Counterclockwise means when you go around, you go the direction against the clock. Suppose instead of a region R like that, that's enclosed, that's without any holes, I have a hole in the middle. But the hole is actually traversed clockwise. So if I go counterclockwise around the inside and around the outside, but clockwise around the inside, so then this is a nice way of thinking of it. The region is always on my left. As I'm going around here, the region is my left, and if I'm going around here, the region is my left. And I found this region, and I say, suppose I want to do the line integral around this curve that's the union of C1 and C2. Maybe I can do that by Green's theorem, and I can. What I do is I think of breaking it up this way. This is the proof of the result here, and then I'll write the result on the next page. To do the integral around C, the union of C1 and C2, well, I need the integral along C1 plus the integral along C2, right? So I go this plus this to evaluate the result along C, the union of those two curves. But that's the same, I'm going to claim, as the integral along C3 going like this, the red, plus the integral along C4 going like this. Why is that? Because the integral along here going this way cancels the line integral going this way. Remember, they're minus each other when you go opposite directions. And the line integral going blue this way and the red going this way cancel each other. So the line integral going around here, oops, and around, plus the line integral going around here is the same as these two. But now Green's theorem applies because these are simple, closed, piecewise, smooth curves going counterclockwise. And so this integral C1 plus integral C2, the line integral, is equal to line integral C3 plus vector line integral C4. And to each of these, Green's theorem applies. So I can take dg dx minus df dy for this one, that's R1, plus dg dx minus df dy for this one, that's R2, but we know from previously that the sum of these two integrals over R1 and R2 is just the integral over the whole area, so we can write that as the single integral dg dx minus df dy over R. So now here's the result for Green's theorem for a multiply connected region. It's got two curves bounding the region. Double integral over the region of dg dx minus df dy that's got a hole in it is the integral counterclockwise around the outside curve plus the integral clockwise around the inside curve. Actually, I should have pointed that out before. Clearly, it's counterclockwise on the outside, clockwise on the inside, so that you keep the boundary always on your left. Well, what happens if the inside curve was counterclockwise, so they're both counterclockwise? Well, that's no problem because this integral clockwise is just minus the integral counterclockwise. So if they're both counterclockwise, you just put the first one minus the second one and you get the same result. So this is an immediate consequence from this region. integral. And then, well, what if I have multiple holes? Well, if I have multiple holes, you just do exactly the same thing with more cuts. We make cuts all the way through here and break it up into multiple pieces. And it turns out if these go clockwise on the inside and counterclockwise on the outside, so the region's always on your left as you move around, then the line integral is the line integral along C1 plus C2 plus C3. You can have any number of holes and just add all the line integrals together, where the ones on the inside go clockwise and the ones on the outside go counterclockwise. So let's try doing that here. Suppose that I wanted to evaluate the line integral counterclockwise around the square that goes from this 5 by 5 square with one vertex at the origin, and its union with this curve on the inside that goes around this little rectangle. Alright, so I want to evaluate the line integral around the union of these two curves. Well, what can I do? Fortunately, they found a very nice region, right? Square and rectangle. So I might be able to do this integral more easily as a double integral. So I applied Green's theorem for multiply connected regions and say the region around this curve that's the union of the C2, of the C1 and C2, is the double integral dg dx minus df dy dA by Green's theorem for multiply connected regions. And now what's dg dx minus df dy if I'm trying to evaluate this integral? Well, it's a nice easy case, despite that this was a terrible line integral with cosine and x squared and so forth. Dg dx partial of this with respect to x is just 4. Df dy partial of this with respect to y is just 1. And so I'm just integrating 3 over the region. I don't even have any work to do, because this is, I pull the 3 out. This is just integral 3 dA, and the double integral dA is just the area of the region that I'm integrating over. Well, that's the area of the square minus the area of the rectangle, so I take 3 times the square's area, 5 squared, minus the rectangle's area. It's a 2 by 1 rectangle. It gives me 3 times 23 is 69. So this double integral comes out to be 69, much easier to evaluate by Green's theorem than as a direct line integral. Few closing comments here. That's actually the important thing, but there's kind of a fun result that goes into here that says if you deliberately choose a vector field f equals x times j, you actually find that an area of a region, a plane region that's bounded by a simple closed piecewise smooth curve, can be evaluated by taking a line integral along its edge. Isn't that kind of a surprising result? If you integrate along the edge of a region, you can figure out what its area is that's enclosed inside. That's exactly what Green's theorem implies here. If you take f equals xj, 0I plus xj, then Green's theorem says, right, area is double integral A. This is the proof again. Dg dx is dx dx, minus df dy is 0, is integral x dy. So this says the area enclosed in a region that's bounded by a simple closed piecewise smooth curve taking counterclockwise is the integral x dy along the boundary. Similarly, I won't write this, you can look at it if you want on your screen. If you choose f equals minus y dA, you get the same result. Integral minus y along the boundary also gives you the area, and then you can average the two of them. If you take 1/2 the first one plus 1/2 the second one, you get this result that's sometimes seen in textbooks: 1/2 x dy minus y dx integrated along the boundary also evaluates the area. So at least 3 different ways to evaluate the area by integrating along the boundary. You can take any weighted average of those two, so there's an infinite number of ways technically. So let's try an example. Suppose I want to find a formula for the area of an ellipse. That was really eluding us before, right? But the result up there, the first one, says that I can find the area by integrating x dy along the boundary of the ellipse. And I know just how to write an ellipse parametrically, right? You let x equal a cosine t, and y equals b sine t traverses the ellipse x squared over a squared plus y squared over b squared equals 1. Remember that result? It's just like you parameterize a circle, x equals r cosine t, y equals r sine t for a circle of radius r. This gives you parametric equations for an ellipse with semi-axes a and b. And you let t go from 0 to pi to traverse the ellipse once, starting here and going around counterclockwise. So if I do that parametric curve and I say by our last result, integral x dy evaluates the area, well, I can evaluate by theorem 1 I presented today, x times dy dt dt, and let t go from 0 to pi to go around once. And let's see, x was a cosine t, and dy dt is the derivative of b sine t is b cosine t. I just have to take ab, which is a constant, out and integrate cosine squared from 0 to 2 pi. Remember how to integrate cosine squared? Use the half angle identity, right, as 1 plus cosine 2t over 2. And that's easy to integrate. You get t over 2 plus a fourth sine 2t. Evaluate at 0 and 2 pi, all times ab, you get pi ab is the area of an ellipse. Nice proof, right? If a equals b, you get pi r squared, the area of a circle, right, or pi a squared. And there's other applications. For instance, centroids of regions can be calculated by this formula, 1 over 2a, the line integral around the boundary of the outside, x squared dy for the same kind of regions. Or minus 1 over 2a integral y squared dx gives the x bar and y bar coordinates of the centroid, a very important point geometrically, we said.